Okay, we're moving into a new chapter today. This stuff comes at us pretty fast, huh? We just finished mesh analysis. Now we're going into chapter 4. And this is actually kind of a high point on the challenging spectrum here. We're going to be asked to kind of look at circuits in a bunch of different ways that, the purpose of this is really to kind of improve our grasp of what's going on in these circuits. But they're going to take us into some pretty abstract category. Question? Yeah, they're coming. Due to a software screw-up, they ended up going over to physical science. I redid them over here, and Scott will be bringing them over in a little bit. Yeah, just it should be done in a few seconds. So the first part is just going to be an overview of what's going on here. So yeah, I mean, I noticed like the lab yesterday, I think I saw a lot of light bulbs going off with people kind of finally getting what a node voltage is. When you're measuring that in the lab, it kind of makes sense, right? You're putting a voltmeter across 2 points in the circuit and you're seeing what it reads. That's the node voltage. And until you make that connection, a lot of this stuff is really abstract. These topics are taking us further into the abstract domain. We're going to do a lab involving some of these, I think next week, yeah. So again, you'll kind of find an excuse to appreciate what these things mean when you're actually working at the bench level of circuit. And so this is a collection of circuit theorems. The first one is linearity, and what you can do with linearity. This is a property that you first kind of hear about in physics, right? What do you hear about linearity in physics? Well, I guess you hear about it in math too, but it's an important property that results in things like superposition. Have you heard of superposition in physics? You didn't talk about superposition in physics. You guys never got superposition. Matthew's nodding. What does it mean? Philly talked about it?
No, I feel like
you feel like you did? Well, it means like, well, it's this additive property, basically, of linearity. But, well, I'll just sort of explain it. So this linear relationship between cause and effect kind of stems from the fact that much of our components have this nature where, like, there's a line here, right? You have Ohm's law, which has a linear relationship between volts and current, which is the slope of that curve, which is R. And so what that means is you have this homogeneity thing, right? Well, if V equals R times I, and of course that also means that I equals G times V, that the homogeneity principle says, all right, well, so V equals R times I, and what does that mean? Well, that means that if we have some current I2 that equals twice the current I1 in a circuit, right, at some point in a circuit, or through a resistor, right? If you just take some resistor and you're applying some current to it, and you get some V1 out of it, right? Then if you apply another current to it, you have an I2 current, and you get a V2. Well, it's pretty obvious that V2, which is going to be R times I2, is going to be, you can substitute I1 in there. It's R times 2I1, and that gives you 2RI1, which gives you 2V1. Is that something to, like, shock you out of your complacency? I mean, it's kind of obvious, right? That when you have a linear relationship like that, you can, if you double the current, you're going to double the voltage across a resistor, right? And yet this is actually kind of useful in statics when we were solving some problems like, what's the highest load this system of cables can support. You know, I was telling you, well, so this is a linear system, right? You can just assume, you can put a load of like 50 pounds on the system and figure out what the forces are in the cables. And then if you still have a lot of extra room, you can, you know, if you end up having a load in your cable of like 100 and the cable goes up to 200, you can double the load, right? Because everything's going to scale proportionally. Well, that's the homogeneity principle, and the additivity principle is, let me see if I can get Scott. Where are those handouts? Of course, the printer's probably breaking down, because every time I print something over there, it kills the printer. Let me see if I can get Scott. I may have to have somebody run down to physical sciences, grab them from there. Let's see what's going on. Not answering. It's probably because he's hitting the printer right now. You can keep going, right? You can scratch this on your notebook, right? We're going to get handouts eventually. So that's the homogeneity principle. The additivity principle is that, okay, so what about the additivity? Well, if V equals R times I, and again, this is not terribly crazy, and I maybe is the sum of I1 plus I2. You can break the current down into like the sum of two other currents. Well, then that means V is going to equal R times the I1 plus I2, if that's what I is, right? And that means it equals R times I1 plus R times I2. But what are those? Well, that's just V1 plus V2, right? And this is what's often called superposition. What's the English expression of superposition? Superimpose. What does that mean? Putting one thing on top of another, right? Well, the precise definition of superposition is something like this. It's like the response to the sum of two inputs is the sum of the responses to those inputs taken separately. Does that make sense? So if you know the response to you know, an I1 input to the resistor is V1, and the response to an I2 input is V2. And if your input, if you're going to now add I1 and I2 and put those both in, then your output's going to be the sum of both outputs, right? V1 plus V2. So that actually, again, doesn't seem like a super, you know, powerful tool, but we can use that in circuits that have like a lot of sources. And what that means is you can like, if you have a circuit with like 3 sources in it, you could turn off 2 of the sources and do the effect of at a particular point in the circuit from one source. You figure out what that circuit variable is, and then you could turn off that and then turn on the other source. You turn on the sources one at a time, and you find the response to each of those sources, and then you find the total response by adding those responses together. That's superposition. All right, I guess I'm going to have to send out a search party. I think I'm going to go. I thought I was recording. Well, I might have missed the beginning of the lecture. I thought I was recording. We're talking about these circuit theorems. We're talking about linearity, linear relationship between cause and effect. If you talk about something as the input and the output, if you're inputting a current, you're getting a voltage. I probably just paused while I went to run and get the handouts. Anyway, we are solving this problem, and we're going to use nodal analysis. And so the nodal equation, I'm just going to do this real fast, is this should all be familiar, Vs minus Va over R1 plus Is, thank you, plus 0 minus Va over R2 equals 0. That's the famous nodal equation for the Va node, right? And you can get common denominators. So if you multiply this whole thing by the product of R1 and R2, you can find that you're going to get Va times R1 plus R2. We're kind of jumping ahead here. kind of skipping some of the grinding algebra. That's going to equal R2 times Vs plus R1 R2 times Is. And you can solve for VA then as equaling R2 over R2 over R2, 2 over R1 plus R2 times Vs plus R1 R2 over R1 plus R2 times Is. And the solution to the problem, which is the current in the resistor R2, which we're going to just say, let's just call that I2, is that I2 is going to equal VA minus 0, right? This node voltage divided by R2. Because, right, this here is VA. When you label that node, right, that here is VA. So the final result is that, dividing by R2, that I2 is going to equal Vs over R1 plus R2 plus R1 over R1 plus R2 times Is. Okay, everybody with me so far? That is the solution. Any questions on that? Because we're going to look at that now in a slightly different way, and we're going to bring in this notion of superposition, which we talked about. Debbie? How'd you get from VA to I2? Well, VA is a node voltage. And what that node voltage means is if you hook up a voltmeter to that node, as you found in the lab yesterday, right? And you hook up the common port and the V here, you're going to read VA on your display. That's the potential difference between the top node and the reference node here at the bottom, which we're calling 0, right? And so the potential drop from this node to here is going to be VA volts. And that happens to be the same potential drop that's going across the R2 resistor. And so Ohm's law will tell you that I2 equals VA over R2. This is Ohm's law. How does this help us in any way? Well, the interesting thing about this, you can dissect this thing and say, well, wait a minute. Suppose I just had, redrawn this circuit where I had R1 and R2, and I just conveniently disconnected the current source from where it was in the circuit originally, right? I just have a blank there where the current source is. And essentially what I've done is I've replaced the current source with an OC. What's an OC? Isaac, what's an OC? Gotcha. Original content. Yes, I've replaced the current source with an original content. Matthew, what's an OC? Orange County? The OC, right? Colin, what's an OC? Mason, what's an OC? An open circuit. Yeah, replace the current source with an open circuit. Okay. So that's essentially turning off a current source. And had I done this, does this sort of, do you see the connection between, say, this and that? What is the connection? If we're talking about I2. you see that basically this term on the I2, this thing that I've circled here, this term right here, is basically what you would get if you didn't have a current source in that circuit. You just pulled out that current source and figured out what the I2 was with just a voltage source alone. That you would actually have Vs over R1 plus R2. Okay. That is sort of the inkling of superposition there, right? If you just turn off the current source, you can find out what the current is just from the voltage source alone, right? Now, taking that another step further, suppose we had redrawn that circuit and where that voltage source is, we're just taking it out and we've replaced it. We replaced the Vs with an SC. David, what is an SC? Yes, a short circuit. And we put the current source back in. We still have our R1 and our R2. And now we're still trying to find what's the I2 here, but we don't have a voltage source anymore. That this is essentially the I2 that you would get from the current source. And in case you're not familiar with that version of the current divider formula, try this: 1 over R2 over 1 over R1 plus R2, 1 over R1 plus 1 over R2 times IS, right? That's the G2 over G1 plus G2 formula, which devolves. These are actually the same thing, just using some algebraic thing. In fact, if you sort of divide, or if you multiply the numerator and the denominator over R1 plus R2, you're going to get the same thing. So that's telling you that, again, this is the superposition principle, right? You can basically find the current I2 by turning off the sources and just having one on at a time and finding the result from each source individually and then adding the two results together. That's superposition. You can do that because of what principle of circuits allows us to make that happen. It's the principle of linearity that makes this happen. And this comes up in a lot of physics situations. You'll see this happening. It probably comes up in physics 3C when you work with waves and stuff, because waves in a linear form, they'll actually be additive. And you can do all kinds of interesting stuff with that. The response of a circuit due to multiple sources can be taken as the sum of the effects of each source acting alone with all other sources turned off. And so turning off sources means you're replacing a voltage source with a short circuit, in which case the Vs equals 0. We call that a short circuit. And a current source with an open circuit, a current source that's set to 0, is just like an open circuit. Why is a voltage source equal to 0 the same as a short circuit, anyway? Why is this the same as turning a voltage source off? Well, what's the voltage drop from here to here when you have a short circuit there? It's 0. So that's how you can impose a 0-volt drop across 2 points of the circuit. And so that's like turning off a voltage source. You're assigning that thing to 0. Unfortunately, you can only do this with independent sources. Dependent sources have to be left on and in the circuit because they are responsible for something. You know, they're responding to some other part or some other variable in the circuit. You cannot leave those off. They always have to be on. Mason? If there's dependent source, if there's a dependent source, depending on a source that you have turned on, you can't turn it off. Is that what you're saying? Yeah. Yeah. Well, can you have a dependent source that depends on an independent source so that when you turn off the independent source, you've also turned off the dependent source? Sounds like a tongue twister. You can follow that. You're in good shape. but the dependent sources are never dependent on independent sources. They're only dependent on like certain voltages through a resistor, or currents through a resistor. Although thinking about your question, I suppose that's true. Let me just think about it, because like if you had a resistor here and a voltage source, and this was like the control voltage for, but that would be an illegal, you can't, yeah, maybe. I'd say maybe. But yeah, generally the dependent sources are determined by, the circuits are complicated enough that they are, they're going to be left in the circuit, because they're going to possibly be, it may be that the, just having a particular source can't trigger it. So it really is, it's really context. Basically, you have to look at the problem. Yeah, so we're going to do just a simple one without dependent sources, and then we are going to do one, example 2, which is going to show one with a dependent source in it. You can kind of see how that works. So we have this circuit here. We want to apply superposition to find the current in a 3-ohm resistor, and this is your goal, I 3 ohm, or just call it maybe I3, or I guess it's I3 ohm. Because we have 3 sources in that circuit. And the fun thing about superposition is it makes you look at the circuit in a lot of different ways. And why is this actually helpful? We'll actually sort of talk about that maybe after we do this. Somebody remind me to say that if I forget. We're going to start by just looking at the effect of the 4 amp source only. The 4 amp source turned on. You're going to have the 1 ohm, the 2 ohm, and the 3 ohm resistors. And we're turning off the 5 amp source, so there is an OC there. And we're turning off the 6 volt source, so there's a short circuit there. And we're trying to find I1, which is the contribution of the 3 ohm current that is just due to the source number 1 being on. So we still have our 4 amp source. And when you do that, what famous circuit type is being shown here that we can use to solve for I1? What type of circuit pattern is this? This is where it pays to kind of memorize those things. What is that? It's a current divider. And so you can use that current divider formula to easily find the current there, right? So it's a current divider. So you can say, well, this resistance is, the current is being divided through this resistive path, which is 5 ohms, and this resistive path, which is 1 ohm. And so the current divider equation says that I1 is going to equal 1 over 5, because that's the total path of that resistance, over 1 over 5 plus 1 over 1 times 4 amps, which is going to equal 2/3 of an amp. And it might be helpful because sometimes some of these sources might have the current going in another direction, but let's draw that arrow going down, because that's the direction that we're talking about for I1. So in other words, the total current going through the 3 ohm resistor is going to be the sum of the current from these 3 different sources once we turn them on one at a time. And just the contribution from that one 4 amp source is 2/3 of an amp. And then again, with the 5 amp source turned on and everything else turned off. So let's do it that way, 5 amp source on. means we're going to draw this circuit. And we've got just these terminals here where that 4 amp source was, because it's turned off. It's an open circuit. We've got the current source going this way. And our resistor, oops, that was just a voltage source. That's still a short down there. And we have 2 and 3. 5 amp source. And what kind of circuit pattern do we have in this case? A current divider. Again, another current divider. In this case, you know, we're going to call this, again, we're going to keep the same orientation, so I2 is also going down, right? And the current divider equation in this case says that I2 equals, again, well, it's going to be minus, because you can kind of see that the current's going to be flowing the other way, right, up through that thing. Can you get to see that, right? The current's going to be going that way or that way. That's the division. So it's going to be minus 1/5 times, or divided by 1/5 plus 1/1 times the 5 amp source. So that's going to equal minus 5/6 of an amp also going down. But because it's minus, that means it's really going up. And then finally, with the 6 volt source, I'll do this in purple. With the 6 volt source turned on, and the other guys turned off, you're going to have something that looks like this. Oops, we're going to call this not I2, but I3. And what kind of circuit do we have here? Could be a voltage divider if you're trying to find the voltage across a 3 ohm resistor, but we're not. We're actually just trying to find the current through it. So it's basically just a series, you know, it's a voltage source in series with 3 resistors, right? So what's I3, the contribution from that 6 volt source? Mark? Go straight to the answer, 1 amp, right? It's 6 volts over the sum of all those series resistors, right? 1 plus 2 plus 3. So that's going to give us 1 amp, yeah. And so therefore, we've got all these 3 different things. Let's go to one final color here, maybe maroon here. Taking all this information, we can say that the total current through the 3 ohm resistor, that says through. In other words, the I3 ohms that we're trying to find is going to equal the sum of all 3 of those things. So it's going to equal 2/3 minus 5/6 plus 1. And it has a net of 5/6 of an amp going down. Any questions? Isaac. Could you have a problem with more than 3 sources in it? You could. Well, was it worth the effort to use superposition? Because you got to redraw the circuit over and over again. That's sort of the good question. I will tell you, like, you know, those quizzes that we're doing, you're going to have quizzes. Let's see. Yeah, the next quiz you're going to get is, I think it's the end of next week. Like not this Sunday, but next Sunday. It's going to have a lot of problems, like with maybe 2 sources in it. And the thing is, when you just have 2 sources, it's pretty easy to find using superposition. You can kind of solve it by inspection, right? You could do nodal analysis if you want to, but superposition can kind of get you the answer real quickly. If you've just got like a current divider with one source and a voltage divider with the other, you can just write it out by inspection pretty much, right? Because you understand those formulas and you've used them so much. It can be a really quick way to get to the answer. And, you know, when you're working in the field, or if you're just kind of doing something, you know, and you don't want to sit down and do a whole nodal analysis thing, because, you know, you got systems of equations to kind of deal with. If you can find something just by inspection, it's an advantage, right? Another benefit of superposition is what? What did we learn by doing it, you know, this circuit 3 different ways? We learn the contribution from each of those sources, right? So if you wanted to know, like, which source is actually is providing the, you know, the most impact on that 3 ohm resistor, the answer would be what? The voltage source has the most, you know, influence on it, right? So yeah, if you're trying to like lower the power dissipation, you know, on that resistor, it might help you to know that which one is providing the most, you know, is using that or providing the most current through it. So so that actually can be kind of nice for certain things. Okay, we then have a circuit here with a dependent source. And just to kind of remind you that you cannot turn off a dependent source when you're doing superposition. We're going to solve this, and again, we're going to find it using 2 different sub-circuits. So the first sub-circuit is going to be with the 4-volt source on. So we're going to redraw this. We'll see if this helps us too. It's interesting. Superposition definitely gets you some really interesting views of circuits that you wouldn't normally get otherwise. So this is a 3 times VAB source. And oops, yeah, we have the terminal here, and we're turning off this current source, so there's a big open circuit there. And this voltage here is the VAB voltage. Okay. Now, I guess I should point out, this is actually a situation where people often kind of run afoul when they're trying to solve these things. You've got like a circuit which has a lot of stuff in it, and you're asked to find like the terminal voltage VAB at the end there. And what do you know about, what can you see about this particular circuit? What's interesting about that circuit? Does anything kind of pop up on how might you find VAB? How might you go about finding VAB? Isaac?
I know there are problems like this on quiz, like find like one side.
One side or the other. It's sort of like that, but it's still just one loop here, right? It's one. There's that circuit is just one loop in that circuit, right? But there's a break in that loop. So what does that tell you? Open circuit. What does that tell you? What's the current circulating around that loop? 0, right? Mason.
So when we see that, like the A and B come up,
Yeah.
so we assume that there's nothing after that.
You assume there's nothing after that. Yeah. Do we assume when you have the A and B like that there's nothing after that? I mean, there could be, you know, something going on there, but yeah, you're not given anything, so you just assume there's nothing after that. If there was something after that, then, you know, then the current going through that thing might not be zero, right? So no, you're just looking at what's given to you. You don't assume anything else might be. So that is a deduction that you have to make when you see a circuit like that. You have to deduce that, well, because you have an open circuit there, that the current throughout that whole thing is zero. You might want to underline that or put some star by it. Whoa, it's zero, right? Because you have to infer that from the circuit. There's no like Ohm's law that's going to tell you that that's zero. It's just you've got a loop of components that isn't quite connecting. So you can't have current flowing across that boundary. So the I is zero. Isaac. Does that mean that the voltage across a specific element would be zero? Yeah, and specifically the resistor, right? So that means when you do KVL, you know, you can say, well, KVL is going to equal, you know, you're going to say -4 plus, well, the voltage drop across the 10 ohm resistor is 10 times 0, right? Plus 3 VAB plus VAB has to equal 0. And so therefore, VAB is just going to equal 1 volt. Is it easier to solve that subcircuit than the one above? Yes, it's simpler to have only one source in there. So the superposition kind of allows us to break the circuit down into smaller chunks that might be easier to solve independently than to do the whole thing together. Isaac. Would we be done? No, we're not done yet, right? Because we have to do the other one. What's the other subcircuit? What do we have to do? We're going to turn off the voltage source, right? So with the 2 amp source turned on, we get a circuit that looks something like this. Okay, and looking at this, what kind of deductions can we make about what's going on in this circuit? What do you see? What pops out? Can you use the fact that you already know what VAB is? That's really good question, but it's not a good idea. Why? Well, VAB may be different. The dependence, this is actually another thing that some people kind of, you know, when you start doing super, they assume, well, the VAB that I found when the voltage source was on is going to be the same VAB I found when the current source is on. But that's a dependent source. It depends on everything else that's going on in the circuit. So when you change the circuit in some way, you turn off a source, everything changes in the circuit, and so does the dependent source, right? So yeah, you can't use that number again. Isaac. When you're done, you're going to add them up, yeah. Probably not, yeah. Probably wouldn't make sense to make it the same. But what can you infer? It's just a simple thing to infer from this circuit, just the way it's currently configured. Mark? The current everywhere is 2 amps. because you got a 2 amp source in that circuit. So you still have one loop, right? So the current everywhere in that loop, if you got a current source in that loop, is going to be forced to be 2 amps, and it's going in this direction, right? It's going this way. It's going this way everywhere, right? Again, these are the things you kind of have to kind of pull out, tease out of the circuit as you're looking at this thing, staring at it and going, oh, we got a 2 amp source there. Okay, so everywhere it must be 2 amps. And for passive sign, we would label the plus and minus this way, right? Yep. Mm-hmm. Yep. When I turn off the voltage source, it's still connected, but when I turn off the current source, it's disconnected. My notation in the symbol, in the circuit symbol, right? Yeah, that is intentional. That's because when you turn off a voltage source, the voltage goes to 0. And the way we model a 0 voltage drop is by putting a wire across 2 terminals, because they're now, you know, when you have a conductor there, they have to be at the same potential. So the voltage difference between these 2 terminals is 0 volts, and that's what we get when you turn off a voltage source. When you turn off a current source, you make it an open circuit, because by doing that, the current through that source, from that source, is 0 as well. Current across an open circuit is 0. And that's what forces the open circuit, the current of 0 being out through that whole circuit. Yes, you can think of a turned off voltage source as an empty branch. Well, it's a short circuit in the circuit. I don't like calling it an empty branch. I guess an empty branch, you're talking about like a wire that doesn't have a component on it. I guess you could call it that. Mm-hmm. It's a short circuit because what? It's putting a wire across the terminals where that device was. You're not depleting it, you're actually just connecting 2 ends together. It's not I don't know. Okay, yeah, it's 0 volts instead of whatever it was. Yeah. Yeah. Okay, we only have 2 minutes. We got to finish this thing. So how are we going to solve for VAB now? Well, KVL again would be a pretty good idea. KVL, and you know, we can go clockwise again, even though the current's going, the loop is circulating, the loop current's circulating counterclockwise. But because we've labeled the pluses and minuses, you know, we got the plus and minus here, we got the plus and minus and the plus and minus. We'll say basically that minus 10 times 2, right, because we're hitting the minus sign first on that resistor, plus 3 VAB plus VAB equals 0, right? We know the voltage drop across that current source is VAB. It's labeled for us. So VAB is going to equal 20 over 4, which is going to equal 5 volts. So the total current for VAB is going to equal 1 volt plus 5 volts. I mean, the total voltage, not the total current. Total voltage is going to be the sum of those two, which is going to equal 6 volts. Questions? Matthew.
So even though we took out in the first one, we took out the 2 amp current source,
Yep.
the voltage, I guess, across where that would be.
Yeah. So in the first one. Yeah, so the question is, even though we took out the current source here in this example, we're still labeling that voltage VAB. Mm-hmm.
But if there wasn't like the terminal right inside, would we not be able to, I guess we wouldn't have to.
Well, if those terminals weren't there, they might have, they might have just, I mean, whether the terminals are there or not, VAB is sort of implied to be the voltage drop across that current. Do you agree? Yeah. But calling them the terminals A and B kind of makes it clear what VAB is. Yeah. Mike, Mason? It is a, yes, it's a voltage dependent voltage source. Yeah, that would actually answer your question, right? Yeah, if you had a current controlled voltage source, then the dependent source would go to 0 in that first circuit when you turn off the current source. So yeah, you can, it's definitely context dependent, right? You have to look at the circuit and make those deductions. So it requires more understanding, right, to make this stuff work. And so this is where this chapter gets a little more demanding. Yeah. Great. So we're going to continue tomorrow.